everybody. Today we're going to be doing the second half of our linear programming lesson. We're going to be doing two problems from start to finish. You'll notice there's some information up top. We do have a table for us in this problem, but if you flip to the next page, you'll notice we won't have any sort of information organized for us. We just have to do everything on our own. Okay, so we're going to start with something like number 4. This is actually a good model for any linear programming problem where you break it up into parts, starting with let statements, our objective, our constraints, and so forth. Okay, so let's go ahead and read the problem together. So it says your factory makes fruit-filled, typo, that should have 2 L's, fruit-filled breakfast bars and granola bars. For each case of breakfast bars, you make $40 profit. For each case of granola bars, you make $55 profit. The table below shows the number of machine hours and labor hours needed to produce one case of each type of snack bar. It also shows the maximum number of hours available. So let's analyze what they're actually asking in this problem. Ultimately, we're going to be finding, and actually this is usually written up top. It's going to say find the optimal number of cases of breakfast bars and granola bars. Okay, now you'll notice that they mention profit in this problem. If profit is mentioned, your goal is probably going to have to do with the profit. But we'll talk more about that when we get to it. So when we look at this table, we're told that the number of machine hours for a case of breakfast bars, okay, and that was noted up here. So it takes 2 hours on the machines to make the breakfast bars, and granola bars take 6 hours on the actual machinery required. We'll write case. So on the machinery, it takes 6 hours to produce. Now we have a maximum of 150 machine hours. You'll notice these are all lined up in one row. That means they all have to do with the machine hours. Okay. Now the reason for this maximum, if you put yourself in the shoes of a business owner, maybe you can only run the machines for a certain number of hours because otherwise they'll break down too quickly. Okay, so that would be a really realistic situation. Likewise, labor hours. So it takes 5 labor hours to make a case of breakfast bars and 4 labor hours to make a case of granola bars. And the maximum number of labor hours is 155. Now that's, again, a very realistic constraint. A lot of times when you're a business owner, you can only assign a certain number of hours per week because obviously you have to pay people. So you can't just have people work an unlimited number of hours. That is a limitation. Okay. Now we're going to start by talking about our let statements. So remember that let statements mean let x equal and let y equal. So your variables are always going to be the thing that you're producing. So let x equal the number of cases of breakfast bars and let y equal the number of cases of granola bars. Okay, pretty straightforward. And now we can move on to our objective. So what is our goal in this problem? So our objective is going to be to maximize profit. Now we know that because if you look back up to the original problem, they're telling us about profits. Okay, so it's never a situation where you want the least amount of profit. You always want to have the most. So our profit equation comes from the fact that we're making $40 per case of breakfast bars and $55 per case of granola bars. So remember that our X was the breakfast bars, our Y's were the granola bars. So it's going to be 40X plus 55Y. Okay, now with this objective function, we don't do anything with it until closer to the end of the problem, okay? Now at this point, we can jump to our constraints. What is limiting our production? Well, we're limited by the number of machine hours and the number of labor hours. Now you'll notice this table makes things a lot easier for us because it's really organized. We know that 2x plus 6y has to be less than or equal to 150. So our machine hours, this whole row, is going to go into an inequality. So we've got 2x plus 6y has to be less than or equal to 150 because we can only work up to 150 hours on those machines. Now, our labor hours is our second constraint. We have to be less than or equal to 155, and these two numbers go with the number of cases of each item. So we've got 5x plus 4y is less than or equal to 155. Okay. Now our last couple, and we talked about this the other day, is that x and y have to be positive values. Okay, now we're not going to worry about graphing these bottom two because notice that we're already in the first quadrant, so we don't really have to worry about that. But now I do have to graph the other two constraints. So when we're graphing here, I like to use the cover-up method, and I'll have my calculator with me just to make these calculations easy. Let's start with, we'll use a couple different colors. Let's start with this top equation. Okay, the x-intercept comes from covering up the y. So we have 2x equals 150, x would equal 75. To find the y-intercept, cover up the x. So we've got 150 divided by 6, and we have 25. Okay, easy enough. Now, before we graph anything, I'm going to do the same process for my second equation. So let's do this. Okay, covering up the y to find the x-intercept. We have 31. And our y-intercept, 155 divided by 4, 38.75. Decimals are perfectly fine. Okay. So we want to graph both of these lines, and I'm going to graph them using the intercepts. Now I have to mark the x-axis. So let's see if we probably can go by fives. Let's see. The biggest number I have is 75. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. Yeah, so 75 would fit. So let's do every 2 tick marks is 10. Okay, and let's do the same thing on the y-axis. You can keep the same scale. Really, we only need to go up to 40 because it's the biggest y value we have. All right, so let's graph each of these. So in purple, my x-intercept is 75, my y-intercept is 25, and I'm going to draw that line connecting these two. Now to figure out the shading, remember it's about testing a point. If I test 0, 0, which is underneath this line, plugging 0 in for both of those values, 0 is definitely less than 150. So I'm going to shade toward 0, 0. So I'm lightly just going to shade this whole region. Okay, and so we're done with that first inequality. Now we're ready to move to the second inequality. We're just going to eyeball these values. So 31, let's say, is right over here. 38.75, a little bit before 40, and cross these 2 points. Okay. So kind of went a little bit too far, so let's just clean that up just a bit. Okay, so again, testing 0, 0 in this inequality. 0 is less than 155. So again, I'm going to shade towards 0, 0. And you'll notice that the overlapping region is this section right over here. So I'm going to shade that in just a little bit darker so we can see exactly that feasible region. Okay. Now you might notice that we've got a few intersection points for this feasible region. I've got 0, 0. So there's my first one. I've got 0, 25 right here. Make that a little darker. I've got 31, comma 0 right over here. And I have this last one. Now I can probably guess the coordinate. My graph is pretty accurate, so it looks like it's at 15, comma 20, but I want to show you guys how to find the actual intersection point. Okay, so I'm going to use my calculator here. And to do that, actually, the first thing we have to start with, I'm going to do the work right below. Let's see if we've got some space. I want to get both of these equations into slope-intercept form, okay? So I'm going to start with the first one. We've got, I'm going to move the 2x over. So I've got 6y equals negative 2x plus 150. I'm not worried about the fact that it's an inequality because I just care about the slope-intercept form. So I'm going to divide by 6. Okay, so this is one of our equations. Let's do the same for the second one. Divide by 4. Okay. Okay, so I have two equations that are in slope-intercept form. Remember, we're looking for the intersection point. Now that's something that our calculator can pretty easily do once we plug the equations in. So I'm going to go into y equals, clear that out, and write in my first equation. So I'm going to use parentheses around that fraction. So I've got negative 1/3 x plus 25. And my bottom equation, we're going to type that in too. And we'll go ahead and hit the graph button. Now clearly we don't see a whole lot besides this little bit over here. And the reason is my graph is just not big enough, right? So I need to zoom out a little bit. Mine was going from 20 to 20, but let's go a little bit further. Let's say we're going to, let's say about 30 in the x direction. And then we'll go 30 in the y direction as well. So we're just zooming out a bit. And so now we can clearly see that our graph is pretty accurate. Now we don't have any shading on here on the calculator, which is perfectly fine. I don't care about the shading. I just need to know where that intersection point is. So we're gonna go into calc. So you hit the second button and then calc. Number 5 is intersect, okay? So I'm gonna hit enter 3 times. And you'll notice it gives us the intersection point at 15, 20. So my graph was pretty accurate. I usually recommend that you guys double check in your calculator, especially if maybe your lines aren't perfect on the graph, okay? Now, we saw yesterday that the reason why we need these corner points is because our objective function up top will always be maximized at one of these values. So we're going to plug all of these into, the objective function. Okay, now the reason why I wrote it below is because I'm just going to use the same space I have here. We're going to do the profit for each possible combination. So our first combination says, okay, we've got 0, actually let's label our variables here. So our x-axis was cases of breakfast bars. Okay, and our y-axis was cases of granola bars. Okay, so our first possible combination says, okay, what if we make 0 of each? Well, clearly, if you plug 0 in, you're making 0 profit. Okay, so we know we're definitely not going to choose that. Now, let's go ahead and plug the following values in. I like to just do them all at once. Okay, so let's see what we get for each of these. We've got 55 times 25, profit of $13.75. A profit of $12.40. And finally, a whopping $1,700. So if we're trying to get a maximum profit, it appears that having 15 cases of breakfast bars and 20 cases of granola bars would be our optimal situation. And so we just did an entire linear programming problem from start to finish. So just to summarize the process, it's always about assigning your variables, determining the objective function, writing our inequalities for the constraints and then graphing them, finding the intersection points of your feasible region, all of those corner points, and plugging them each back into the objective function. And that will lead to your final answer. Okay, now we do have another problem on the second page. I do want to challenge you guys to try it on your own first. I'm not crazy about the wording, so I'm going to clarify just a couple things for you. Actually, let me do this first. Let's read it together. So on a typical long distance call, you talk for 30 minutes. On a typical local call, you'll talk for 10 minutes. Your phone company offers a low rate of $8 per minute for long distance, cents, 3 cents per minute for local. And you have to spend at least 240 minutes on the phone per month, okay? So your parents have set a limit of no more than 15 long distance calls and 30 local calls, okay? So we need to figure out how to minimize our phone bill, how many long distance calls and how many local. So first, let's actually break this down a little bit. I want to see if you guys can come up with just the let statements. Your objective. function, and maybe the constraints as well. Constraints can maybe be a little confusing for this one just because the information is all over the place. It's not organized in a table, but give it a try on your own. I'll pause the video here, and when we come back, I'll have the answers for the first two, and then we'll talk through the constraints. Okay, so I have our let statements here. We're talking about the number of long distance and local calls. Our goal is to minimize the cost. So I went up to the problem and I said, okay, where did we talk about cost? And it was only these two portions. So while we're at it, I'm just gonna cross that stuff out, okay, because we're done with that information, okay? Now, what are we limited by? So the first thing that we're limited by is we're told the company will only offer this deal if we spend at least 240 minutes on the phone. Now, that means we can spend more time than that, but we cannot spend less. So we know that this is gonna come, so we have to spend more than or equal to 240 minutes total. Now, this 240 is a combination of long distance calls and local calls. So we need to figure out how long are we spending on each of those. Now you'll notice up at the top, it says 30 minutes per long distance call and 10 minutes per local. So that means if I combine those, we would have 30x plus 10y. That would be the total number of minutes that we're spending, and it has to be greater than or equal to 240. Okay. Now our other constraint, actually let's cross that out as well. So we use the 30 minutes, we use the 10 minutes. The only thing left, and 240, we use that. Our parents said we cannot spend more than 15 long distance calls or any more than 30 local calls. Okay, so that tells us that we have 15 long distance calls. And actually, let's do this. I want to label my axes while I'm at it. Number of long distance calls, number of local calls. Okay. So we know that we can't spend more, we can't have more than 15. So X would have to be less than or equal to 15. Okay. And we also know that X has to be greater than or equal to 0. So I like to include that in the same portion. You don't have to. You could write it separate as X is greater than or equal to 0. Now, our second inequality is about those local calls. So it has to be between 0 and 30 because our parents gave us that limit. So can't have more than 15 long distance, can't have more than 30 local, okay? And so now we're ready to graph. I'm gonna pause this for just a minute, and you guys can try to graph on this grid. I would recommend figuring out the x-intercepts first, x and y-intercepts of this first one, just so you can determine the tick marks. We'll be back in just a minute. Okay, so I found the x and y-intercepts for the first inequality. So my x-intercept was 8, my y-intercept was 24. And based off of the other numbers as well, I decided to just do tick marks every 2 units. So 2, 4, 6, 8, 10, and so forth. Okay, so for the first inequality, I know that the x-intercept is 8, right over here, and the y-intercept is 24, right over there. And so we are going to draw that line. Something like that. And when we plug 0, 0 in, so plugging 0 in for both of these says 0 is greater than 240. That is not true. So I need to shade away from 0, 0. So I'm going to shade over in this direction. Okay. Now, our next inequality says x is less than or equal to 15. Remember that this is a vertical line. And our next one is a horizontal line. So if I have x is less than or equal to 15, I'm going to go to 15 on my graph, just right over here, and draw a vertical line. Something like that. So it goes up and down forever, but we're just worried about x values that are less than 15. So I'm going to shade to the left. Something like this. And our next one is a horizontal line at 30. So I'm going to draw a horizontal line at 30. And we know that we have to be less, so I'm going to shade below. So you'll notice that our shaded region is this shape over here. In between the purple and the blue. I'm just going to shade a little bit darker so we can clearly see it. So it is this like 5-sided figure, kind of like a cut off rectangle almost. And our intersection points will be 1, 2, 3, 4, 5 of them. Okay. So lucky for us, we can just find the intersection points by looking at the grid. So what I want you guys to do is take those 5 intersection points and plug them into our objective function. I'll give you guys just a couple minutes to do that. Okay, so you'll notice that for each of our 5 intersection points, we found the total cost. Now, if we're talking about minimizing our total cost, the smallest number here would be having only 8 long distance calls. And so that would be our final answer. Notice we have 8 long distance and 0 local. So that would get us the best possible financial situation. Okay. Now for the homework tonight, I updated a new version of the homework worksheet. So if you guys are still looking at what was in the notes packet, disregard those. I actually made the worksheets a little bit easier to go through the problems. They're a little bit more organized. It is still 2 pages, so make sure you do both pages. And if you have any questions, feel free to come in during office hours and we can go through some stuff together. All right, guys, have a great day.